Hello everyone. In the previous video we have seen how to train the usual ordinary least squares regression model using Scikit-learn library of Python, and in that demonstration we have utilized the Boston housing dataset. We'll use the same dataset for today's demonstration, and in this demonstration we are going to focus on regularized or penalized regression models, which include ridge regression, lasso regression, and elastic nets regression models. This video particularly focuses on that of ridge regression implementation, but lasso regression and elastic nets regression models will be explained in the future videos. In the usual ordinary least squares regression, the estimated parameters are assumed to be blue. That means they are best linear unbiased estimators. Here best stands for that the parameter estimates have minimum variance, and unbiased is to indicate that the expected value of the estimated parameters equals to that of the true value of the parameters. So in the OLS regression, the aim was to find the value of the parameters so that the sum square of error or the mean square of error is minimized. However, the mean square of error is the sum of two different components which are usually conflicting. One is the variance of the parameter estimates, and the other the bias of the parameter estimates. So these two components are in opposite direction. That means parameter estimates with minimum variance may have a larger bias, and parameter estimates with minimum bias may have a larger variance. However, by introducing a small amount of bias, the gain in the reduction of the variance of the parameter estimates could be maximized. Then in that case, the total mean square of error could be further minimized than that of the usual the mean square of error estimate of the ordinary least squares regression. So ridge regression is a type of biased regression model that adds a penalty term to that of the sum square of error that the ordinary least squares model aims to minimize. And specifically, the penalty of ridge regression is the L2 norm of the parameters. So in the OLS regression, we are interested in minimizing this sum square of error, but now in the ridge regression, we need to add a penalty, where this penalty is a function of that of the parameter estimates. So the penalty is alpha times the sum of the square of the parameter estimates. So if this component is larger, that means the penalty is higher, but if this component is smaller, the penalty is lower. And specifically, if this component is 0, that means the ridge regression and the OLS regression would be the same. And in matrix form, this objective function can be written in this form. So here alpha is a hyperparameter that should be specified first. It is not a parameter that is going to be obtained when we model, rather it should be pre-specified in order to estimate or train the model. So here, by introducing a small amount of bias, the gain in the variance reduction is going to be assumed to be larger. So this may in fact decrease the performance of the training sets, but the gain in the generalization will be larger, or the gain in the test performance will be larger. And large values of the parameter estimates, due to here the squaring process, large values of the parameter estimates are penalized more than the smaller values, because here we have squaring. Therefore squaring a large value will make that large value extremely large. So due to this squaring process, large values are more penalized than small values. In such case, the parameter estimates will be attracted towards 0, or these parameter estimates will shrink towards 0. So That's why these penalized regression models are also called shrinkage methods or shrinkage regression models. And usually in the usual OLS regression model, we assume that the input features are not collinear, but in the case if there is multi-collinearity, this ridge regression would be more appropriate than the traditional OLS regression. So now let's implement the ridge regression modeling. First, we need to import the ridge function from that of a scalar linear model. So I can execute this cell. Now this function is imported. Now we have to instantiate the model or that of the container of our model using just ridge and assign, let's say, the object name ridge reg. So let's call that assigned object here. Now here it is an orange colored display. So here if we look at the parameter submits, here we have what you call alpha, and this alpha is actually 1. So this ridge parameter or shrinkage effect is alpha, and by default it is assigned a value of 1. And this is just the container for the ridge regression model that we are going to fit. So if we point to here the symbol with like I, it says not fitted. So we just created the container, but the model is not fitted yet. And if you are interested to look at the documentation, you can click on the symbol with a question mark, and you can look at how to model this ridge regression model. So here we have the parameter alpha, which is the ridge effect, and we have also other parameters like that of the OLS regression. Then once we create this container ridge, next we can supply the train input features data and train output data to that of the fit method. So this trains the model using these train input features and train output data. Now it becomes blue, that means the model is trained. If we point to here, it says fitted, and the parameters are the same, just alpha, for example, is 1. Like that of the OLS regression, we can extract that of the estimated parameters, which is the Bayes term or constant term, using the attribute intercept underscore. So the estimated intercept is 26.76, and we can also extract the estimated weights associated with the covariates using the attribute cof underscore. So these are the weights associated with each of the input features included in the model. And we can also assess the training and testing performance. So in the ridge regression model, we need to call the method score, and we have to supply the data that we need. If we supply that of the train data, like here, the score will be that of the training score or training performance. If we supply the test data, then the score will be the test score or the test performance. So if we run this cell, the train performance is 74.16%, and the test performance is 70.4%. So this is how to implement that of the ridge regression model. So compared to the OLS regression parameter estimates, some of these parameters may be close to 0 due to the penalty that is assigned here, which is 1, because this penalty forces the coefficients to go close to 0. And the other here, when we assign this penalty term alpha this penalty term alpha. So if the variables are not in the same scale, this penalty will not be fair, or this penalty will not be balanced across the different covariates or input features. So there is a need of either standardizing the input features or normalizing them. So for this purpose, there are different standardization methods. For example, standard scalar and minimax scalar. Let's import it from sklearn preprocessing. And for now, let's use as of the minimax scalar, which scales each of the input features into a value between 0 and 1. The standard scalar also can be used, which transforms each covariate data into a distribution having a mean of 0 and a variance of 1. But for now, let's use this minimax scalar. So once we import this minimax scalar, we need to instantiate an object of this minimax scalar. Let's give the object name transformer. So if I execute this one, now this transformer or minimax scalar is instantiated, or an object container is created. Now if we point to the I symbol, as usual, it says not fitted. It's just a container for our transformation or minimax scaling, but it is not fitted yet. And if you are interested to look at the documentation, you can click on the question mark symbol, and this opens the minimax scalar documentation. So once we create this minimax scalar, we can look at the parameters. For example, here it says feature range. When the covariates are transformed, the feature range will be between 0 and 1. Here by default, the feature range is between 0 and 1. If we are interested, we can actually specify these two other values, something like 0 to 2 and so on. But by default, this transformation or the minimax scalar will transform each covariate into a value between 0 and 1. And then once we create or instantiate our transformer, next we can supply that of the train data in order to transform the input features. So here the transformer is instantiated. Then after that, let's transform the actual training data frame. And for that, we need to call our object transformer, which is already instantiated. And on that, we need to call the method fitTransform and supply the training input features data. Then this will provide the normalized data frame. Now each of the input covariates in the X-train DF are normalized into a value between 0 and 1. But the original data frame, this one, was having some values like, let's say, 6.43, 58.7 and so on. But all of these values are normalized into a value between 0 and 1 here. Let me remove this one. And now first we have to transform the train data sets using this fitTransform method of the transformer object. Now in normalizing our data frame, the minimum and the maximum value of each covariate is going to be obtained. This minimum and the maximum value of each covariate is going to be used to normalize that of the train data frame. So for normalizing the train data frame, instead of fitTransform, we are going to use transform, then the test sets. Therefore, this will utilize the minimum and the maximum of each covariate that are obtained from the train sets. Therefore, we have to keep in mind that for the train sets, we need to use fitTransform. For the test sets, we have to use that of the transform method. So if I execute this cell, these are the transformed test data. So once we transform this inputs features data X train and that's of X test, we can train our model of interest, which is a regression. So as usual, let's instantiate the regression model using reg, and let's assign regreg scaled, and after that we need to call the method fit on this regreg scaled object and supply that's of the normalized input features and that's of the target variable. So if I run this, now the model is trained and the parameters are as usual here. By default the reg effect is 1.0 or it is 1. So on this normalized data, let's find that of the R-square performance on the train sets. So this will provide an R-square value of 73.9%, and for the test set it provides an R-square value of 71.1. So let's consider, or let's compare these R-square values between the scaled and the unscaled datasets. In the unscaled datasets, the train R-square was around 74.2% and the test R-square was around 70.4%. Basically, let's find the difference between the train R-square and the test R-square. Now the difference is around 3%, which are very close. So let's see again here. Sorry, here I think we need to rerun again here because I used the same name here. Yeah, I use the same name here, regitrain R-square, test R-square. So I'm calling these values over there. So these values are actually for the that's of the model with the model that's trained with that's of the scaled data. So this is around 3%, but let's see or train again these models. The original using that of the unscaled data frame. So let's train this one again, and we can obtain the R-square value, yeah, and this one, and here the difference between the two. Okay, it's 0.037 and yeah, it is 0.02. Therefore, compared to that of the unscaled data, the scaled data has a better performance, which is not an overfitting. For example, in the unscaled data, the train R-square is 74%, the test R-square is 70%, so it seems that there is a slight overfitting problem when we use that of the unscaled data. But when we use that of the scaled data, now the train R-square decreases. That means the overfitting problem is a little bit contained, and it is very close to that of the test error with a percentage of, let's say, 2.8%. So in general, standardizing or normalizing the input features for ridge regression problem is required. Otherwise, the penalty associated with the different covariates with different values may not be fair. So now, instead of focusing on a single value of this ridge parameter, something like here 1, it is better to explore how the different values of the shrinkage effect affects the value of the regression coefficients or the regression parameters. So for that purpose, let's import this matplotlib pyplot as PLT, and matplotlib, I have to run this one. And now for the by default, here the ridge parameter considered was 1, but we can consider any non-negative value, and we have to find the optimal value that yields the best performance in terms of training and testing sets. So here let's explore different values of this ridge parameter, which is the alphas, and plots and see how the increase or decrease in the shrinkage effects affect the value of the regression parameters. So first let's show this here. NP log space, let's say -3 for 10 means just generating an evenly distributed 10 values between 10 to the power of -3 and 10 to the power of 4, that is from 0.01 to 10,000. So if I run this one, it means the minimum value is 0.001, that is 10 to the power of -3, and the maximum value is 10 to the power of 4, that is 10,000. Therefore np.log space is nothing but generating 10 values within the interval between -3 and between 10 to the power of -3 and 10 to the power of 4, and these 10 values are also evenly distributed. Similarly, if we make it 20, these 20 values which are evenly distributed between 10 to the power of -3 and 10 to the power of 4 will be selected. So for now, let's consider 100 values. 100 values. So these 100 values starting from 0.01 to 10,000 are going to be considered as ridge effects. That means we are going to model 100 models considering a shrinkage effect of 0.01, 0.001177, and so on up to 10,000. So here we have the alphas as NP log space -3 for 100, and we are going to collect the ridge coefficients, and we are going to use this simple function to see or to plot and examine how the shrinkage effects affects the value of the parameters. So if I run this, the plot will be something like this. Therefore, for example, if the shrinkage effect is 0.001, one parameter will have a value around -20, and another around -15, and some around -10, and one around -5, and some of them will have a value near to 0, and some around 5, and there will be one parameter estimates around 20. But if we increase the shrinkage effect, let's say to that of 10 to the power of 1 or 10, now the values are close to 0. If we further increase the value of this shrinkage effect to, let's say, 10 to the power of 3, almost all the parameter estimates are close to 0. But if we make it 10,000, then definitely all of the parameter estimates are 0. Therefore, increasing the shrinkage effect forces the parameter estimates to close to 0. That is why this rigid regression, lasso regression, and elastic net regression are called shrinkage methods or shrinkage regression models. Now, of these different values, for example, we have considered 100 different possible values for the ridge parameter, but of this we have to select the one that has a better performance in terms of train and test sets. So let's use what we call hyperparameter tuning, using the function grid search CV. If I click on the grid search CV, it opens lots of the grid search CV documentation, and you can look the details here in this documentation. So for example, the first input is the estimator, that means the model of interest. For our case, we are going to use that of the ridge regression. And here the param grid is nothing but all those possible values of the hyperparameter. And you can also look the other parameters in order to specify this grid search cross validation. So first we have to instantiate our model of interest, which is our estimator. So that's the ridge regression. Let's instantiate. Now as usual, this is just not fitted, or it is just a container or instantiation of our model of interest. And next, let's determine the possible values of the shrinkage effect alpha as NP log space minus 3 for 20. Instead of 20, let's use 100. Therefore, there will be 100 possible values for this shrinkage hyperparameter. And that means 100 models are going to be fitted. Of those 100 models, the one that performs best is going to be selected. So now our param grid consists of alpha with these different values, with these different 100 values, starting from 0.01 or 10 to the power of minus 3 to 10 to the power of 4 or 10,000. So we need to import this grid search function from scalar model selection. So I can run this. Now this function is imported. Then we have to use this function grid search CV. It has parameters. The first is the estimator. Our estimator is the ridge rig. Here, the ones that we have instantiated here. And the param grid is nothing but the ones that we have defined here. A dictionary consisting of the name of the parameter alpha. This is the parameter in the ridge regression model. Therefore, the name should be alpha. This is alpha, so this name should be alpha. And possible values of this parameter are listed here. And number of cross validations, let's consider 10 different folds. And to obtain the train score, let's specify it as true. Then we can run this cell. Here we have the grid search CV, and the parameters are the estimator is the ridge regression estimator. The parameter grid is nothing but alpha, consisting of values here. These values runs from this one, from 0.01 up to 10,000, and so on. And the number of cross validations here, the ones that we have specified is 10. Here it is 10. So now this grid search CV is still instantiation using that of our instantiated model and the parameter grid. If I point to here, it says not fitted. So to fit for the model, we need to call the method fit over this instantiated grid search CV. This is the instantiated grid search CV. So we have to call the method fit, and we have to supply the train input features and the train output data. And here we are using that of the normalized input features. In all of the regularized methods, we have to consider standardizing or normalizing the input features. So I can run it. Since it is going to fit 100 different models, it may take a little bit some time. Now the model is fitted. If I point to here, it says fitted. And the model is as usual, just the ridge regression, and alpha, the optimal value of these 100 values. The optimal value is found to be 0.79. Then we can extract that optimal value or the value of alpha using the method best params underscore, and we have to call our hyperparameter name, that is alpha. So if I run this, it is 0.79, which is actually 0.79248, 0.79248. And let's see the R square of the model when we use this alpha value, and that R square we can extract using the feature best score underscore. Now that R square is 0.6915. It is around 69.2%. So the optimal ridge parameter is 0.79 and its corresponding R square is 69.15%. And the grid search, this trained grid model has also another attribute called CV results underscore. This is a dictionary. We can easily convert it into a data frame, but this data frame has a large number of columns, so it's not easy to visualize. But let's see. So this is actually a dictionary, but a dictionary can be easily converted to a data frame for ease of visualization. So if I run this, it has the mean fitting time, standard deviation of fitting time, mean score time, and so on. The parameters, that is the ridge parameter in our case, the split test score for split 1, for split 2, for split 3, and so on. So here there are different columns, so it may not be easy to visualize, but of these different columns, it's better to extract only the value of the hyperparameter, that's param alpha, mean test score, mean train score, and let's extract that of the rank of the test score. So if I execute this one, it provides this one. Then here we have 100 values. Of these 100 values, the one having a minimum test score is the value of alpha, which is 0.724. Now here by default some of the values are hidden here, so it's not easy to visualize, but let me consider here just 50 to, let's say, 80. Okay, so it's 3 now, so let me say from 30 to 50. Yeah, so the parameter value of alpha that yields the better performance of mean test score of 69% and train test score of 74% is 0.79. So 100 different models are fitted for each of the possible ridge parameter values. And the other, typically we may be not that much interested on the estimated value of the ridge parameter, but we may be much more interested in the uncertainty over the estimated value. So it is essential to look at how much variability is there both in the training and test sets of the cross-validation scores. And for this purpose, we need to write certain function, something like this. So let me simply run it. Sorry. So this shows the variability in the train and test scores. So for example, here the orange solid line represents the mean test score and the blue solid line represents the mean train score. So for example, for the mean test score, the range starts somewhere from here, let's say from 0.5 to around 0.85. So the variability is higher for smaller values of the shrinkage effect, and the variability becomes smaller when the shrinkage effect increases. Therefore, in general, as long as the value of the shrinkage effect is larger, the variability in both the train and test scores will be close to 0. But at certain time, just for the smaller values, the variability is higher, but for large values, the performance of both the training and test scores will close to 0. That means the model will have very poor performance, because the parameter values are all going to close to the value 0. So the variability in the test score is actually larger, but the variability in the train score is somewhat smaller. But when we increase the shrinkage effect, both the variability in the train and test scores will close to 0 due to the enforcement of all the parameters to that of the value 0. So lastly, we have obtained this optimal value 0.79. So let's fit our model using this ridge parameter 0.79. So we have to replace here, we have to instantiate the model ridge. Now we have to add the parameter alpha 0.79, and then we have to fit our data using the train input and output features data. You can run. Now the model is trained using that of the hyperparameter of the ridge effect 0.79. Then we can obtain the training score and testing score of this model 0.74 and 0.71. So here the differences are around, let's say, 3%. Therefore this regression performs well, like that of the wireless regression model. So this is all about today's video. In the next video we will look at how to implement lasso regression and elastinate regression models.